Good morning. Shamakra, can you hear me?
Yes, yes.
Good. I'm just testing my microphone. Okay. Today we will start new chapter. That's chapter 4. And hopefully next week we'll talk about chapter 5. That's all for this course. So this chapter 4 is about eigenvalues and eigenvectors. One of the most, how to say, central or important concepts in linear algebra. Okay, so what we have here we have 4 subchapters that we are going to learn here. So introduction to eigenvalues and eigenvectors. In part 2 is 4.2. We have to study determinants because eigenvalue problems are related to determinants. We need to know how to compute determinants. And in 4.3, eigenvalues and eigenvectors of n by n matrices. And 4.4, similarity and diagonalization. And 4.5 and 4.6, I will skip these subchapters since we have very short time, and these are the most important concepts here, 1, 2, 3, 4. So you have to study for these subchapters, and you're going to have quiz from this next week. Okay, so now let's talk about eigenvalues and eigenvectors. First, actually, its meaning, it's a German word. It's taken from German language. And it means that eigen means own or characteristic of something. That eigenvalues and eigenvectors are characteristic of a matrix in the sense that they contain important information about the nature of the matrix. So when it says, say, important information about the nature of the matrix, what do we mean by this? I mean, actually, as we actually go through this chapter, you'll have more understand the idea about these concepts, and as you also solve more problems, you'll gain deeper, how to say, intuition about this concept. Just to understand, when you just say that it contains information or important information about the nature of the matrix. What do you mean by this? I just give you one example, not about this, but when I just use that word, what do you mean by that word? For example, you know that this ax squared plus bx plus c is equal to 0. What is it? It's just a quadratic equation. And to solve this one first, and as you know, we need to find this discriminant, that is delta. Delta equals b squared minus 4ac. Okay, this is 4ac. And also here, this discriminant, it really carries important information about the solution of this quadratic equation. Because we know that if delta is greater than 0, if delta is greater than 0, we know that this equation has 2 real roots and they are distinct. They are not equal to each other, and these numbers are real. And if this delta is equal to 0, for example, we know that it has 2 real roots and they are equal. And how about if delta is less than 0? It has 2 roots, but they are complex. These are complex numbers. Something like this, because sometimes when we just say that it actually gives us information about the nature of this equation, then you may understand what we mean by this, okay? So as we actually go through this chapter again, we'll get more, how to say, intuition about this concept. Anyway, let's start with this definition first. It says that let's A be an m by n matrix. So here we are talking about n by n matrices only. A scalar lambda, so this lambda is a real number, is called an eigenvalue of A, the matrix A here. If there is a non-zero vector, that's important, that's non-zero vector because we are looking for non-zero vector x, such that Ax equals lambda x. Such a vector is called an eigenvector of A corresponding to lambda. Okay, actually this is the eigenvalue problem, and as I said, it's one of the most central problem in linear algebra, and it has applications throughout mathematics and in many other fields as well. So here actually we are going to talk about just this equation, this particular equation. Here we have lambda and x. Now if I ask you, for example, how do you solve this equation, let's say in real number system, Ax is equal to Bx, for example. How to solve this? Just take this to the left hand side. Ax minus bx is equal to 0. And x is a common factor. A minus b times x is equal to 0. So to solve this one, either we have two cases. A minus b should be equal to 0. We don't know actually they are equal or not. Or x is equal to 0. Now, if I actually solve this equation, I'm looking for x. Now, if you just consider this case, then how many solutions does it have? If this a minus b equals 0, then x is any real number because 0 times anything is equal to 0. And if a is not equal to b, the only solution is, actually here, I should not, maybe I should consider in two different cases. Number one is a minus b is equal to 0, and a minus b is not equal to 0. If the first case, if a minus b is equal to 0, then x is any real number. It has infinitely many solutions. And how about if a minus b is not equal to 0? Then the only solution is non-zero number times what is equal to 0? The only solution is equal to 0. So here we have only one solution. And it is obviously, I can see that it's actually not difficult to find this solution. Actually, this solution is of not our favor. We are not actually, we don't need such solution. In this case, actually, we are interested in this. Okay, if a is not equal to a is equal to b, so what are those solutions? So actually here, it is something like this. In eigenvalue problem, here we are talking about matrix. Here we have A is a matrix, n by n matrix, and X is n by 1 vector. Here, what is it? It is n by n matrix, and X is a vector from n-dimensional space, and lambda is a real number. We're just considering this problem. So in this similar way, actually, we solve this, but here, our concept is, actually involves, the problem involves matrix. That's why we need to know the properties of matrices. So here, to solve this one in a similar way, I should just take this to the left-hand side, and here we have 0 vector. The 0 is from n-dimensional space here. Now, I should factorize this. X is a common factor. So if I take this x out, what do we have here? A minus lambda, and here we have identity matrix. And here we have x vector. And on the right-hand side, we have 0 vector. And some people, they may get confused. Here, lambda is just a scale, a real number. And this one is n by n matrix, right? To make sense, actually, here, you should put I, otherwise it doesn't make sense. So here we have that equation. And here, since we are saying the non-zero vector, if this x is non-zero, the only way is this a minus lambda I, right? This a minus lambda I, that thing should be equal to 0 matrix, right? It should be 0. I mean, this matrix is, if it is 0, it's always 0. So here, sorry. Let me just denote this thing by b, and here we have b times x is equal to 0. So what is it? It is a homogeneous system, right? A homogeneous system of linear equations here. So now we know that actually if b is invertible, that means it has inverse, you should just multiply by actually just using the fundamental theorem of algebra. That means that if b is invertible, it has only one solution, right? That is 0, because just multiply both sides by its inverse, then x is equal to 0. Actually, that means here it's this case. I don't need this 0 solution, because here in the definition we are saying that if a non-zero vector exists that satisfies this equation, right? Then we call this an eigenvector. So at the time, to have this system, this homogeneous system, to have non-trivial solution, this b must be not invertible. So that means that soon actually we will see that when actually it's not invertible, it means that it has more than one solutions. Anyway, that is a kind of problem that we're going to deal with in this chapter. So now to understand more, let's see a few examples. In this question, it says that show that x, this vector, this actually it's a vector, right? 2 is an eigenvector of this matrix, and find the corresponding eigenvalue. So what color should I use here? Maybe I should use white, it's much better. Solution. So here we're talking about again this eigenvalue problem that ax equals, here we have lambda x. This x and this x, it is a vector, right? So in this question, a is given here. That is, matrix A is 5, 2, 2, 5. And here our vector, it is x1, x2. And here lambda is not given, is show that x is an eigenvector of this one. So here, that means that actually that thing is equal to some kind of scalar times this vector. Right. Okay. So how can I show this? Actually, this x1 and x2 is given. Maybe I need to write here, not x1 and x2. I need to write here 2, 2. And also here, it is 2 and 2. Okay. So now we know that actually it's the kind of system here, right? If I just take this to the left-hand side, what do we have here? Here we have, okay, here we have 5 times 2, it is 10, plus 2 times 2, it is 4. Here we have 9. 2 times 2, 4. 5 times 8 is 9. And take this to the left-hand side, minus, here we have 2 lambda and 2 lambda. And on the right-hand side, what do we have here? 0 vector, 0, 0. Or, as see here, what we have here, 9 minus lambda. 9 minus lambda should be equal to 2 lambda, should be equal to 0. The second one is also the same. 9 minus 2 lambda is equal to 0. Exactly the same equations. So from here, lambda is equal to 9 over 10. So find the corresponding eigenvalue. So if this x is an eigenvector of this matrix, then it is corresponding eigenvalue is this, 9 over 10. That means that actually here, what's going on here? And we know that actually multiplying a vector by a matrix, it is a linear transformation. So this transformation is simply transforming this x, right? It's a vector on itself. Not itself, it's onto another parallel vector. So that's maybe this one is our vector, this one is x, and what is lambda x? Maybe lambda x is this vector. This one is lambda x. So how can I transform this vector onto this vector? By just using this matrix. Anyway, this is just first, let's work on the technique, how to find eigenvector or eigenvalue. This one simple example. Here in the other example, in example 2, it says show that 5 is an eigenvalue of this and determine all eigenvectors corresponding to this eigenvalue. But here, we are given that ax is equal to lambda x, right? So here a is given, a is 1, 2, 4, 3, and x, I don't know. Let's say its components are x1 and x2. On the right-hand side, what we have here, lambda, and here we have, actually also we know lambda. So I can write here 5. Here we have x1 and x2. Okay, that means that to find this eigenvector corresponding to this eigenvalue, we need to solve this system. Because as you see here, if you just simplify this, we'll get the system. So on the left-hand side, what do we have here? Here we have 1 times x1, 2 times x2. So here we have x1 plus 2x2. And here we have 4x1 plus 3x2, right? And if you just take this to the left-hand side, minus, here we have 5x1, 5x2. On the right-hand side, we have 0 vector. Okay, so now if you just simplify this, what we got here? Actually, maybe I should not solve this in this way. Here, I can just solve this in our using Gaussian elimination methods. Another way is, look, here we have ax equals lambda x, right? To solve the system, here we have a minus lambda I, and here we have x is equal to 0 vector, right? And to solve this one, as you know, actually we need to solve, we need to reduce this augmented matrix, right? Here we have 0 vector into reduced row echelon form. So let me just use this method. So if you just do so, what we have here? Here we have this matrix, right? And here we have 5. So that means that here we have lambda is 5. What is 5 times I? 5 times I is, this one is, here we have matrix. Let me just simplify here. But matrix A minus, okay, here we have A minus lambda I. That is, what is A? 1, 2, 4, 3 minus, and multiply identity matrix by lambda. So here we have lambda 0, 0, lambda, which is equal to, here we have 1 minus lambda. So here we have 1 minus lambda, 2 minus 0, that is 2, 4 minus 0, that is 4, 3 minus lambda, it is 3 minus lambda, right? So now that thing is equal to this. So now if you just reduce this to reduced row echelon form, we need to find, what is it? Even we know lambda, right? So if we know lambda, since lambda is equal to 5, then A minus 5 times I is equal to 1 minus 5 is equal to minus 4, 2, here we have 4, and here is 3 minus 5 minus 2. And if you just reduce this to reduced row echelon form, here we can divide by minus 4. So here we have 1 minus 1 over 2. And divide by 4. Here we have 1 minus 1 over 2. They are exactly the same, right? If you just multiply the first row by negative 1 and add to the second row. So here we will get 1 minus 1 over 2 and 1 minus, 0. And here we have 0, right? So from here, if you just write the corresponding ordered system, what do we have here? Here we have x1 minus 1 over 2 x2. That is equal to 0, right? So that means that x1 is equal to 1 over 2 x2. So here, then what is that eigenvector? Because that x is our eigenvector. We are looking for this. Let me just write it this way. So then eigenvector corresponding to this eigenvalue is x1, x2. And here, what is x1 from here? x2 equals 2 times x1. So here we have x1, and x2 equals 2 times x1, which is equal to x1 times 1, 2. Okay. So now, actually, what is x1? x1 is anything, right? It can be any real number. So actually, you'll just attach a special link to this. So now, if you just get any vector from this space, let me just call this for now. Actually, you call this eigenspace corresponding to this eigenvalue. What is our eigenvalue? It is 5, right? Actually, this here we have these vectors. And these are spanned by this, vector, 1, 2, right? Because here, scalar multiple of this vector. So if you just pick any vector from this space, it will serve as an eigenvector for this matrix. All right. So now, let's just give to the a name to that. What is that space? Because as you see here, the set of all eigenvectors corresponding to an eigenvalue lambda of that matrix A is just the set of non-zero vectors in the null space of that thing. It is A minus lambda times I, because here we are solving the system, right? So we are just looking for non-zero solution. Non-zero solution means all the solution vectors in the null space of that thing, right? That gives us the eigenspace. So it follows that the set of eigenvectors together with the zero vector in Rn or here in R2, is the null space of A minus lambda I, right? Null space of A lambda I. So now let's just give a name to this. Let A be an m by n matrix, and let lambda be an eigenvalue of A. So the collection of all eigenvectors corresponding to lambda, together with the zero vector, we are just also adding this zero vector, because otherwise it cannot be subspace, is called the eigenspace of lambda, and is denoted by E lambda. Actually, just set up all these numbers. As you see here, in this example, here the actually how many such vectors exist? Infinitely many, right? Because if x1 equals 1, you get one vector. X equals 2, one vector. Actually, they form a kind of subspace here if you just add 0 here. So I'm just writing here eigenspace corresponding to this eigenvalue 5. It is this set. It contains all the vectors. When you just substitute into this equation, it satisfies this equation, because also 0 is always a solution. That's why we are also adding 0. Okay, immediately let's see another example related to this. Given that, okay, here we are given 3 by 3 matrix. Is 1, negative 2, 1. I mean, a vector whose components are 1, negative 1, and 2, 1, an eigenvector of A. First, we have to answer this question. If yes, find the corresponding eigenvalue. So this thing is eigenvalue of this or not. How can I show this? Here, if this vector is, let's say it is x, so this A times x, is it equal to some scalar times x? Can you just find this lambda or not? Good. The question is this. So we are looking for lambda. Or if you just evaluate this, A times x, I mean, is the result just lambda scalar multiple of this x? All right, let's just show this here. So here we have A times x, which is 3, 6, 7, and the 3, 3, 7, and 5, 6, 5. And our vector here, 1, negative 2, 1, which is equal to 3 times 1, 3, 6 times negative 12, it is negative 9, plus 7, it is negative 2. And 3 times 1, 3, 3 times negative 2, minus 6, so it is minus 3, plus 7, it is 4. And 5 times 1, 5, 6 times negative 2, negative 12, so it is negative 7, plus 5, negative 2. So actually they have a common factor, all of these components. What is it? It's negative 2. If we just take this negative 2 out, what do we have here? Here we have 1, negative 2, and is equal to 1. So now that's our original vector. This one is vector x. And also we got the same thing here. What do we got here? Here we have negative 2 times x. And here we have this lambda is a scalar, it is negative 2. So since this ax, I mean, it's just transforming this x, actually, this matrix is transforming this x into another vector which is parallel to this vector, because this is parallel, right? It's just scalar multiple of x, that means they are parallel. So that means that this vector is an eigenvector of this A. So what is its eigenvalue? It is negative 2. Okay. So find the eigenspace of this eigenvalue. So here we are saying that this eigenspace, let's say it is E negative 2. That means that it's eigenspace corresponding to this eigenvalue. What we have here, we have a lot of vectors here, and we know that if you just pick any vector here, right? So what is that eigenspace then? That eigenspace corresponding to this what is it? Corresponding to this eigenvalue negative 2 is here, it is just span of these vectors 1, negative 2, 1. Okay, any scalar multiple of this vector will serve as an eigenvector of this what is it, equation. Okay. Another example, show that lambda is equal to 6 is an eigenvalue of this matrix, and find a basis for its eigenspace. solution. Let's use different color, how it looks. Okay, not bad. So first we have to show that this lambda equals 6 is an eigenvalue of A. So that means that here we have A times X is just equal to 6 times X. Right? So it means that such vector exists, non-zero vector exists, because A is given here. For the 6 to be eigenvalue, we should be able to find a non-zero vector X, so that when we just multiply that thing by A, right, it should be the same as 6 times X. So here, to find this one again, to solve this, as you know, if you just take to the left-hand side, what we have here, A minus, here we have 6, and here we have I, and here we have X is equal to 0. And what is it? It is a homogeneous system. And we know that by just using Gauss method or Gauss-Jordan method, so I need to write augmented matrix. Since on the right-hand side it's 0, the last column is 0, I'm just not going to write this. So what is just A minus 6I? So that is, here we have, okay, actually you should notice here that this 6I means, here we have 6, the 6I means it is something like this. It is 6, 0, 0, 0, 6, 0, 0, 0, 6. So if you just subtract this matrix from this A, it means that we need to subtract this 6, right, this lambda from the components in the main diagonal. So that thing will be equal to, here we have 7 minus 6. It is 1, and other components do not change. So it is 1, 1, negative 2. Here we have negative 3. Here we have 2, 2. Here we have 6. And 3 minus 6, that is minus 3. And 2 minus 6, that is minus 4. Okay. So now if you just reduce this, now here, also imagine that here we have 0 column, that augmented column here. So the first thing is, as you see here, if I just multiply the first row by negative 3 or just 3 and add it to the second row, 3 plus negative 3, 3 plus negative 3, negative 6 plus 6 is 0. So it's 1, 1, negative 2. Here we have 0, 0, 0. And also if you multiply the first row by negative 2 and add it to the third row, here we have negative 2 plus negative 2 is equal to 0. Negative 2 plus 2 is equal to 0. Here we have 4 plus negative 4. So here we have 0, 0, 0. Right? So that means that actually from here, since we have one row, that means that 1, 0 row, rank of this one is less than 3. That means it's not invertible. So it has a non-trivial solution. So from here, if you just write the corresponding linear equation, then that one is x1, x2, x3, right here. Don't forget that this x is not this x, or this x is a vector from 3-dimensional space. That is x1, x2, x3. So here we have x1 plus x2 minus 2x3 is equal to 0. 3 variables and what is it? One equation. So here we have 2 independent variables, right? So let's say here from here, let's say x2 equals s and x3 is equal to t. Then what will be x1? x1 will be minus s plus 2t, right? So now if you just write that vector, then what is vector x? Vector x is, here we have x1, x2, x3. So here we have x1, what is x1? Minus s plus 2t, x2 is s, x3 is t. Or I can just write it as s times, here we have negative 1, 1, 0, plus t times, because s and t are just scalars. Here we have 2, 0, 1. So these two vectors are linearly independent. So what is the question here? Show the lambda is, equals 6 is an eigenvalue. So we have already shown that for this lambda, we have corresponding eigenvector, which is not equal to 0. So that is this vector right here. And find a basis for its eigenspace. And what is the basis? So basis for eigenspace is this. Here we have -1, 1, 0, and here we have 2, 0, 1. Right? And also you can just write here, what is the eigenspace of this 6? That is just span of these two vectors, -1, 1, 0, and 2, 0, 1. Okay, that's it. Not so complicated. Just write here the first answer, the second one, and this one is the third one. So find the eigenvectors and eigenvalues of A geometrically. So here, actually it is 2 by 2 matrix, so that means that we are talking about the transformation of vectors from two-dimensional space. So let's say our vector is this. Here we have x and the y. Actually, maybe I can just write different x here. X. Okay. So what is this? If you remember this one, here we have ax, right? That is 1, 0, 0, 1, and here we have x and y. So if you just calculate this, here we have -1. So here we have x and 0x, -y, -y. Right? If you remember, actually, this transformation, what does it do? It just reflects a point about the x-axis. So this one is our two-dimensional space. If you just pick any vector here, p, whose coordinates are x and y, right? So it's x negative y. X negative y is somewhere here. Let's say this p prime, x negative y. That is actually this transformation, just reflecting this p into this. Guys, let me give a break for 2 minutes or 3 minutes. After they will continue. Let me have some rest. All right. So geometrically, so we know that actually it's just reflecting this point about the x-axis, right? So if you just consider it as a vector or the endpoint of this vector, the terminal point, and just reflecting this vector, let's say that is x, and into this vector, right? And as see here, this x, right, and this vector, let's say it is, what is it, vector y, whatever it is. And vector y is not a scalar multiple of this x, right? The only condition that this A reflects or transform this x into into another parallel vector is the terminal point, or this x must be lying on the y-axis. So if you just consider this here, the first case, how about if you consider this point? Okay, whose coordinates are, let's say it is p 0, y. So if you just actually how to say, multiply this matrix, that A transforms this one into this point, where that is P prime, that is 0 minus y, right? So here, what is it here then? If this one is x, then this AX will be just equal to minus x, right? The first case, that is our this vector and this vector. And how about the other case? The other case is if the vector is lying on the x-axis, right? On the x-axis, let's say it is Q, whatever it is, that point. So that thing is X and 0. Now, what is the reflection of this vector of this point about the x-axis? It's just itself, right? So the second case, it will be then, it will be just that AX will be just X itself. So to find the eigenvectors and eigenvalues of this geometrical. So that is a geometric description of this transformation. From here, let's say that eigenvalue, the first one, it is -1. And it is corresponding eigenvector. Let's say it is X. What is it? It is in the form of this. That is 0, Y. Y is any real number. How about here? Its eigenvalue is 1. And the corresponding eigenvector is any vector of this form. Now also here we can just find the eigenspace, right? Eigenspace corresponding to this eigenvalue, -1, -1. It is just span of this vector. It is 0 and 1. And how about the eigenspace of this, the second one, that is 1. It's not 2, it is 1. So that's 1. It is just span of these vectors, 1, 0. That is any vector on the x-axis. The first one, any vector on the y-axis. All right, that's the last slide. After that, we'll have break. So, find all of the eigenvalues and corresponding eigenvectors of the matrix. So here, again, we need to actually here, this is a little bit different question, because in the previous examples, either eigenvalue was given or eigenvector was given. And also actually we're asked to verify that the given vector is an eigenvalue, a vector, or the given real number is an eigenvalue of the equation, the matrix. So here, nothing is given, only the matrix. So if you're given this matrix, how do you find the eigenvectors and its eigenvalues, or eigenvalues and corresponding eigenvectors? To do this one again, we have to solve this equation here. We have A, if we have X equals lambda X. Only here we know A now, right? We don't know X, we don't know lambda. So we are asked here to find X and lambda. So to solve this one again, I can just bring this into this form, right? And here we have X is equal to 0 vector. And also once again, what we have here? Here we have an n by n matrix. This one is n by n matrix. But here in this particular case, let me just write this for this question. Here we have 2 by 2 matrix. And how about here? This X is from two-dimensional space, 2 by 1 vector, or vector from two-dimensional space. And here we have simply this homogeneous system. Here we have something like this: B times X is equal to 0 vector, right? So if B is invertible, once again, we know that actually by fundamental theorem of algebra, it has only unique solution, and the solution is 0, right? Because if you just multiply both sides by its inverse, and B inverse B is I, here we have X, B inverse times 0, that's equal to 0. The only solution is 0. And we know that 0 is not an eigenvector, right? So here, for this system to have non-trivial solution, if you remember this determinant, right? Determinant of A minus lambda I, this must be equal to 0. Because if it is equal to 0, it's not invertible. So it has non-trivial solution. So that is actually, we'll just focus on this more. That is always to solve this eigenvalue problems. This determinant of A minus lambda I should be equal to 0. In the next session, we will actually learn how to compute determinant of any matrix. So here we have 5, 1, 1, 5 minus what we have here, lambda 0, 0, lambda. That's equal to, what is it? Sorry. So let me just calculate the inside. That's equal to, here we have 5 minus lambda. Here we have 1 minus 0, it is 1. 1 minus 0, it is 1. 5 minus lambda, it is 5 minus lambda. So determinant of that thing, right? So then A minus lambda I is just 2 by 2 matrix. What is it? 5 minus lambda times 5 minus lambda, that's squared, minus 1 times 1. Actually, we know how to find determinant of 2 by 2 matrix, which is equal to, if you simplify this, here we have lambda squared minus 510, so it is minus 10 lambda plus 25 minus 1, it is plus 24. So this should be equal to 0 for this homogeneous system to have non-trivial solution. So now if you solve this, here we have minus 6 minus 4. So here we have lambda minus 4, lambda minus 6, that's equal to 0. So from here, the first eigenvalue is 4, and the second eigenvalue is 6. So we have answered the first part of the question. Now, if I substitute there, I can find the eigenvectors, corresponding eigenvectors. So to continue this here, let me just change the marker and continue from here. Let's say lambda 1 is equal to 4. Now we need to find the corresponding eigenvector. What we have here, again, here we need to actually reduce the system A minus lambda I. Here we have 5 minus 4, that is 1, 1, 1, 1. And if you reduce this to reduced rational form, here we have 1, 1, 0, 0, right? So the solution of this one is x1 plus x2 is equal to 0. Now, what is this eigenvector corresponding to this eigenvalue? So here we have x1, and here we have x2 equals minus x1. So it is x2, which is equal to, let's say, x1. Here we have 1 minus 1. In a similar way, how about lambda 2 equals 6? So if you substitute here 6, here we have 5 minus 6 minus 1. Here we have 1, 1. 5 minus 6, it is minus 1. Actually, again, if you just reduce this, here we have 1 minus 1, 0, 0. So x1 minus x2 is equal to 0. Then eigenvector corresponding to this eigenvalue will be, what is it? Here we have x1, x2 equals, and here x1, x2, they are same. So here we have x1, actually just scalar. Here we have 1, 1. In a similar way, you can just write the eigenspace of this, okay? And that is how we compute eigenvalues and corresponding eigenvectors if we are given an m by n matrix. Okay. In the next session now, as you see here, each time we need to evaluate these determinants. This determinant should be equal to 0 for this homogeneous system to have non-trivial solution. And we have already learned how to calculate determinant of 2 by 2 matrix. That's this times this minus this times this. And now we will learn how to calculate the determinant of any m by n matrix. You may be one person to the world, but you may also be the world to one person. Very meaningful quote. Guys, have some rest. After 10 minutes, we will continue. We'll have the second session. See you soon.